Hello and welcome to another video in the integration series from Reigate Maths. This video focuses on integration by substitution, one of the most difficult things typically in the integration section of the second year of the A-level maths content. So when does integration by substitution become important? Well, there are two situations where it becomes useful. One, you're told to use it. Simple as, you're told to use it in the exam. Two, if the thing you're trying to integrate doesn't follow one of the rules that we've looked at in the previous videos, whether that's trig identities, reverse chain rule, or the by inspection method. The nice thing about integration by substitution is that it works for those if you find those difficult. And it also follows a nice method. The thing that students find difficult about integration by substitution is that the method is very long and there's lots of places for you to make mistakes. So we're going to go through an example, and as we go through, I'm going to write out a checklist down the side of our steps. Now this example, I'm aware we could use the reverse chain rule method that we looked at in the previous video. Now quite often, not always, but often, you will be told what substitution to use. Now for those of you doing further maths, in the further maths side of things, in the core pure, that's not always the case. Often you won't get told. But for the maths side of things, typically you will get told what to do. So, step one. Differentiate the u function. Now it might not be in this form. It might be in the form x equal f of u. But regardless, you differentiate it. So we've got u equals x squared plus 1. So if we differentiate it, we get 2x. Step 2. We take the thing we just did and we rearrange to make dx the subject. So we're going to get dx equals 1 over 2x du. Now it's important I've written it this way because of what we're going to do in step 4. So step 3 is substitute. So we know that the integral of 2x, x squared plus 1 squared, is going to be equal to... Now I'm just going to write it on a separate line so it doesn't mess up our checklist. So 2x, can't do anything with that, so let's just keep that there for now. X squared plus 1, that's u. Dx is 1 over 2x times du. So substitute. Step 4. That's not easy, but cancel things out. So cancel and simplify. We can see that we've got 2x here and a 2x in the denominator. Those are going to cancel out. And we're just going to be left with u squared du. Now in other examples, there's going to be sort of intermediate steps here. So there's going to be steps 4a, 4b, but I'll leave those for now. Step 5 for this example is integrate. So u squared integrates nicely. And that's the whole point of integration by substitution, is we turn something potentially unpleasant into something that is very easy to integrate, something that follows a basic rule, in this case, our normal integration. Step 6, substitute back in. Because our original question was in terms of x, we want our answer in terms of x. U is x squared plus 1. And we've got our answer. So generally, if you follow these rules, this kind of series of steps, integration by substitution will be fine. As I said, there's extra steps in here that we'll address in another example or further examples. Also, if we have limits, there are extra steps that we need to do as well that we'll kind of put in here. But we'll address those as we come to them. So let's look at another example. So with this example, we can see that we have a bracket with a power and an x on the front, much like the previous example. So, as we kind of looked at with the previous video, let's have a think. What happens if we differentiate the bracket? Well, we get 1. That is not what's on the front. And there's no way that we can multiply 1 by a number, by a constant number, to get x. So even if we weren't told to use integration by substitution, this is the way you would do this question. So that's something to bear in mind, and what I was saying in the previous example, or the previous video, if those methods, if the reverse chain rule or the inspection methods don't work, you have to use substitution. Because multiplying this bracket out and then timesing it by x and then integrating that whole thing is a bit time consuming. So let's see how we're going to have to adapt that step method that I showed you before for this question. On the whole, though, the steps are the same. We have our u function. So let's differentiate that. Oops. In this case, it's 1. We take our derivative and we rearrange to make x the subject. And then we're going to substitute everything in and see what cancels. So x, can't do anything with that yet. 2 plus x, that was our u. And dx is equal to du. So this is where we now have to add bits to our method. We've still got an x kicking around. If you go back to the previous example, you'll notice that everything cancels out. In this case, it doesn't. So what do we have to do if things don't cancel? So this is where our step 4a comes in. 4a, things don't cancel out. Let's do that in. X's or whatever variable you're using don't all cancel. What we do in this case is we then look at how we can write this in terms of u. Express x or whatever's left. And this kind of step might need to be a little bit flexible. we need to express x in terms of u. Now this is why I tend to lay out my by substitution this way, and I've left myself a gap here, because it allows me to do this step in that gap. Now, very important, only do this if you've got to this stage and you've got x's left over. Things haven't cancelled out. Bear in mind as well, you might not only have x's cancelling out, you might have u terms simplifying as well. So see what cancels, see what simplifies, and then when all the dust settles, do you have any x's left? Then, and only then, worry about this. The reason being, if you try and do this too soon, it tends to overcomplicate the question. But in this case, we've got to this stage, there is nothing more we can simplify. So we have to do this. So now, we're going to substitute that in here. Now this we still can't integrate, but it's not too far off something that is relatively easy to do so. We're going to expand the brackets. Notice how I've kept the integral sign and the du all the way through. That's very important. If you miss that, you will lose marks. Now we have two u terms we can integrate separately. U to the 7 integrates to an 8 u to the 8. 2u to the 6, 2 over 7 u to the 7, plus c. And then, as before, our final step. Put the x's back in. And we're done. Now this is not a particularly nice answer, but it is the answer. And it's not obvious from here that that's what this would integrate to. It's not like the previous example where maybe you could have had a guess or had a kind of gut feeling. This one, it's really not, you couldn't guess it from here. So when you're doing integration by substitution, yes, do think about what's going on and have a kind of gut feeling what it might look like, but be prepared to be wrong with that. It's not always going to turn out the way you want. So these two examples that we've just looked at on the whole cover the method for all types of integration by substitution where there are no limits. Okay, so we don't have any numbers on our integral sign here. Obviously, you may have to adapt this set of instructions. As I said, you may not have this as u in terms of x. It might be x in terms of u, typically if there's trig involved. So you will have to be flexible with this method. It's not a surefire, yes, you will always do all of these steps in exactly the way that the video told me to. So be prepared to think about the question. See what cancels, see what simplifies. Maybe be prepared to use trig identities. That might be relevant. You might have to use some of the integration stuff from previous videos. Be prepared to use everything you already know for this type of thing. The next example we're going to look at, though, involves using limits. So here's our example that involves limits. Use the substitution u equals 2 plus sine x to find the integral of cos x, brackets 2 plus sine x to the 6, with respect to x, between 0 and 2 pi. So, let's follow our normal process. Now, a caveat with this example. Obviously, you could calculate the whole thing without the limits, and then stick the limits in at the end. But again, typically, the point of integration by substitution is to make the algebra or the calculus and the substitution, the actual calculation, far more simple. So we're not going to do that, but bear in mind that's something you could do. But typically, it makes it messier. So we have our u function, and as usual, we're going to differentiate it. Sin x differentiates to cos x. Step 2, rearrange this to make dx the subject. And notice again how I've written it as 1 over cos x du, not du over cos x. That's to try and avoid complications or overcomplicating things when substituting. Now we've got all that, let's substitute. So the thing we're trying to find is the integral. Notice how I haven't changed the limits yet. Come back to that. Or I'm not going to write down the limits. So we've got cos x, can't do anything with that. 2 plus sin x, well that was our u. So we've got u to the 6 times dx, which is 1 over cos x du. And we make things cancel out. Let's deal with the limits now. These, which variable are these the limits for? They're for the variable x. So these are the x coordinates. So these are the x limits. Here, we've got rid of all of the x's. So the x limits are no longer valid. So this will be a step 4b if using limits. We have the limits for x or whatever variable you are using, whether it's x, theta, t, z, whatever. We need to recalculate for u. And again, that's why I leave a space here. So I'm going to do them up here. So we know that when x equals pi over 2, I haven't given myself enough space, but there we go. We know u is 2 plus sine pi over 2, which is, you can't do it in your head, use your calculator. 2 plus sine pi over 2, which is 3. When x equals 0, u equals 2 plus sine 0, which is 2. We can now put these here instead. So now we have swapped from x limits to u limits, which is important because now these are the numbers we're going to put in once we've integrated. Now something very important, doesn't happen often, but it could happen, that the bigger number, the upper limit, calculates a smaller number than the lower limit here. Don't panic if that happens, keep them the same order. And don't worry, it'll sort itself out. So if we had these the other way round, so if when x was pi over 2, we got 2, and when x was 0, we got 3, we'd have 2 and then 3, because those match. Okay? They have to translate across. Don't just swap them round because you're used to having the bigger number on the top. It sorts itself out. Now we're here, we just integrate as we normally would. U to the 6 is 1 over 7 u to the 7, or integrates to. This is 1 over 7 times 3 to the 7 minus 1 over 7 times 2 to the 7. And we just calculate that as normal. So we get 1 over 7 times 3 to the power of 7 minus 1 over 7 times 2 to the power of 7. And it gives us 2059 over 7. And typically you're expected to give your answer as some unpleasant fraction. The nice thing about doing this with limits is that you can check it on your calculator. If we type in this here, again, we're doing trig, so make sure you're in radians mode. We type this in, so we get the integral of cos x. Now the calculator defaults and puts loads of brackets in, so make sure you close all your brackets properly. 2 plus sine x, close brackets for the x, close brackets for the bracket, the power of 6, between 0 and pi over 2. Think about it, and we can see we get the answer here, which again might be a little unexpected. Typically when you have trig, you think, oh, there's going to be pi's in the answer, or there's going to be surds in the answer. Not in this case. So always check it if you're worried that you got it wrong. And that's it with substitution. The teaching bit of substitution is very short. The questions do take a long time to do though. So make sure that you do practice thoroughly. And thank you for watching.